In this video, we'll look at approximating integrals using the trapezoid rule and the midpoint rule. We'll also look at error bounds on those rules. First, we need to find delta x. b minus a, that's 1 minus 0, divided by n. In this case, we'll use 8 strips. So delta x is 1/8. T is, we have delta x, which is 1/8, divided by 2 times f of x sub 0. X sub 0 in this case is 0, so we'll do f of 0. Then notice the inner functions were doubling, so I'm going to pull that 2 out. We'll factor that 2 out. And now we're looking at f evaluated at 0 plus delta x. 0 plus an eighth is 1/8. Then we'll add an eighth again, giving us the function evaluated at 2/8 plus the function at 3/8, and so on. We'll continue that pattern for a bit. F of 5/8 plus f of 6/8 plus f of 7/8. And at this point, we need to close off that bracket. Notice the last function is not being doubled, so we want to close off the bracket. And now we're evaluating the function at 8/8 or just 1. Now we'll use the calculator to approximate that integral. In y equals, we need to type in the function, that is cosine of x squared. And then we'll exit that, go back to the home screen, and now we can type in this part. This can get a little tedious. Feel free to fast forward the video if you already know this part. 1/8 divided by 2 is really 1/16. Times the function. To get that, we'll go to alpha, trace, and then number 1. And we need to type in 1/8. And we need to type in 0 plus 2, open parenthesis, put in the function evaluated at 1/8. And we'll continue that pattern. After we enter this into the calculator, we get 0.90233. And I'll just stop it here for now. Next, we want to find m. We'll use the midpoint rule. Delta x, which we found to be 1/8, times the function evaluated at, we need to find the midpoint of 0 and 1/8. So if we add those together and divide by 2, we get 1/16. So we're starting at f of 1/16. And then we're adding delta x to that. 1/8, if we want a common denominator, would be 2/16. So then we would have f of 3/16. And again, we'll continue to add 2/16. Feel free to fast forward this part. At this point, we will plug it into the calculator. 1/8 times function evaluated at 1/16. And then we'll just continue to plug this in. Again, feel free to fast forward the video. And for this rule, we get M8 is roughly 0.905620 if we're rounding to 6 decimals. Next, we'll estimate the errors in the approximations from part A. In order to find those errors, we need the second derivative. So let's first remind ourselves f is cosine of x squared. Then f prime would be negative 2x sine of x squared. And then the second derivative, here we need the product rule. Negative 2x, that's first. Derivative of the second would then be 2x cosine of x squared plus the second sine of x squared times derivative of the first would be minus 2. Simplifying this, we get negative 4x squared cosine of x squared minus 2 sine of x squared. Now looking at the absolute value of the second derivative, we can just make those negative signs positive. So we have 4x squared cosine of x squared plus 2 sine of x squared. And it may be helpful to remind ourselves that we are looking at values from 0 to 1. At this point, we want to ask ourselves what's the highest value each of these factors can take on the given interval. So we're going to say less than or equal to. 4 is just going to stay 4. But what is the highest value that x squared can take on the interval from 0 to 1? If we think about that graph, the highest x squared can be is 1. And then thinking about cosine of x squared. If you're not familiar with what that looks like, let's graph it really quick. Cosine of x squared, check out the graph. And at this point, let's change the zoom a little bit, or the window. I'm going to make my x min start at 0 and the x max go up to 1. And I'm going to make the y min -1 just so we can be a little below the x-axis and see what's happening. We'll make the y max 2. Looking at the graph, and if we need to, we can hit the trace button to kind of help us see what's happening. The highest value that this function can be is going to be 1. And you may have already known that, but just checking out the graph can be helpful. Plus 2 times sine of x squared. Again, we may need to see that if you're not seeing it right away. Sine of x squared, the highest it can be, looks like it's approaching 1. And if you know your graphs, that makes sense. So we have 4 plus 2 is 6. 6 will be the k value that we use when we find that error bound. K can be any number larger than all the values of this that we just found, the absolute value of f double prime. So we could choose bigger values for k if we wanted, but the smaller the better. This will give us the better error bounds for this example. Now that we have k, we can use the formulas and recall a is 0, b is 1. Looking at the error bound for the trapezoid rule, we'll plug in 6 times 1 cubed divided by 12 times 8 squared. That will give me 1 divided by 128, which if we wanted a decimal, that is 0.0078125. And then the error bound for the midpoint rule, we have 6 times b minus a is just 1, again cubed, divided by 24 times 8 squared. This will give us 1 divided by 256. And if we want a decimal, that would be 0.00390625. Essentially what we just found is the upper limit on the errors that we have in approximating the integral using the trapezoid rule and the midpoint rule. How large do we have to choose n so that the approximations t8 and m8 to the integral in part A are accurate to within 1/10,000th? Let's start with what we know about the error in the trapezoid rule. The formula from earlier, we got 6 times 1 cubed divided by 12n squared, and we want that to be within 1/10,000th. Simplifying that fraction, we'll get 6 times 1 is just 6. 6 divided by 12 is 1/2. And then n squared is still in the denominator. I'm going to write the right side as an exponent, 10 to the negative 4. We can think of that as 1 divided by 2n squared less than or equal to 1 divided by 10 to the 4th. And then since both of those fractions are positive and we have an inequality, we can get the reciprocal of those fractions. That's going to change the direction of the inequality. Dividing by 2 will give us n squared equals, let's see, 10 to the 4th divided by 2 would be 5,000. And then we want to take the square root of that. Square root of 5,000. We get roughly 70.1. So let's round up and say n is greater than or equal to 71. So if we have 71 or more strips or trapezoids, we'll be accurate to within 1/10,000th of the true integral. Now looking at the midpoint rule, earlier we found 6 times 1 cubed divided by 24 n squared. And again, we want that to be less than or equal to 1/10,000th. This time we get 6 divided by 24, that is 1/4 n squared in the denominator, less than or equal to 10 to the negative 4. Again, we'll rewrite that. 1 divided by 4n squared, less than or equal to 1 divided by 10 to the 4th. Again, since both fractions are the same sign, we can take reciprocals, and that's going to change the direction of the inequality. We'll get n squared is greater than or equal to 2,500, meaning n must be greater than or equal to 50. So with 50 or more strips, using the midpoint rule, we'll be accurate to within 1/10,000th of the true area under the curve